thank everybody for joining us today. Today's presentation is Lessons Learned from Texas 2021, the winterization of gas power plants. Our speakers today are Ryan Duffy and Jeff Blair. Ryan Duffy is of Eastern Controls in Edgemont, Pennsylvania. He is the Thermal Division Sales Manager for the Mid-Atlantic USA territory. He is involved in industrial construction industry specific to electrical heat trace and insulation system. Has over 20 years of experience in various roles designing, installing, project management, and sales of electrical heat trace systems. Many of you might know the other presenter, Jeff Blair, an alum of the ISA St. Louis section and the man responsible for putting me in the place on the board originally. So if you don't like me, blame Jeff. But he is also of Eastern Controls now in Edgemont, Pennsylvania. He's a business development director there currently, works with the sales team across the Mid-Atlantic region, developing new customer relationships and providing customer-focused CapEx solutions, beginning in feed and FEL stages. Jeff has over 15 years experience in the life cycle of instrumentation and control sales. He is an ISA senior member and a board member of the ISA New Jersey section. So with that, we're gonna turn it over to Jeff and Ryan. Gentlemen, thanks again for your time today, and please take it away.
Okay, thank you. Well, thanks. It's good to see everybody. So what we'll do, we're going to bounce around a little bit, so I hope nobody gets motion sick. We're going to start the presentation. Ryan's going to head out into our process training unit. We're going to walk through actually heat trace on a flow meter, just to give everybody kind of a 101 look as to what we do and how it looks. Corey, if you can help us, we'll want to make, I guess I stop presenting. I'll stop sharing if we can make Ryan's camera there, the primary.
Correct. Yeah, once you stop, he should pop up.
You're good, Ryan.
Good.
So instrumentation and control. This is what we call our process training unit. And we actually have an active installation. It's in a safe environment. We pump water back and forth, but we've got a heat trace installation on instrumentation like Ryan's showing you here.
Thanks, Jeff. So I'm going to speak a little bit about what we're seeing here in more detail, but so this may be a little bit repetitive, but we do like to, one, show off the PTU, and two, highlight an actual installation of heat trace. So what I'll just show you here is this is one of our fundamental or basic heat trace controllers. In summary, it's a fancy thermostat with a touch screen. It provides a lot of things that are required. For example, 30 milliamp ground fault protection is the most prominent feature of this controller. All heat trace needs to be 30 milliamp ground fault protected. That's typically achieved through a ground fault breaker with a 30 milliamp rating or a controller. We prefer controllers for various reasons, but that's in summary, thermostat providing monitoring as well as control and providing the 30 milliamp ground fault protection. So with a heat trace circuit, I'm going to be really fundamental today. And so if there's any questions that come up, definitely just, speak up and I'll address. But the power is coming into this from your general lighting power, any distribution center that you have. Power is coming into this controller, and then we have an RTD coming out right here, sensing the actual pipe temperature. And then power is coming out based on contactor being closed through this wire here, being fed down through your cable tray over to your power connection kit. This power connection kit is your transition from building wire to heat tracing wire. So a common misconception is that the heat tracing cable that you see here needs to be run back and terminated inside the controller, and that's not the case. The heating cable always stays on the pipe, and this typical component is where you transition again from building wire to heating cable. So you can see here our heating cable is coming out. It's wrapping around. A little bit of an extra loop here because there's a pipe support, and you also have a flange, valves, Coriolis meter, all the way down here, wrapping more valves and supports. And then this is your end seal where you cap off the end of that heating conductor. So in summary, when we size heating cable, what we're doing is we're doing a heat loss calculation along a straight portion of pipe. So for example, let's say we do a heat loss calculation and we're trying to maintain 6 degrees on that pipe when there's 1 inch thick mineral wool insulation, and that heat loss is 4.3 watts per foot, we'll say. What we would then do is choose from the selection of cables we have that is obviously a little bit higher than 4.3. We have a 5, 8, 10, so on and so forth. So we would have a straight run of cable on a straight length of pipe. Now, when you come to something like a support, a flange, a valve, there's obviously a lot more mass there. So that calls for additional heat. So that's why there is an actual wrap of cable. You would never want to go straight across with that cable. It just won't have enough output to keep that additional mass, valve, or whatever that is from freezing. So we get common questions in that customer will call and say, oh, I have 1,000 feet of pipe, so I need about 1,000 feet of heat trace. A typical ratio would be about 30 to 40% more cable than it is straight length of pipe. Typical, sometimes more, sometimes less, depending on the configuration of the piping. But in summary here, you can see we have the cable strapped on, end seal over here, power connection kit. This is a nice short little heat trace circuit that we use. What you're not seeing is any insulation. I will eventually be getting some portions of this insulated just to show that insulation is absolutely required. Heat tracing will not work without any insulation in the piping. But for training and visual purposes, we keep it uninsulated. So I just wanted to show a little bit of tour.
I have a question, Ryan.
Sure.
When Darren Goodland here, whenever you install heat trace, it's all nice when you don't have the insulation, but once it's buried in insulation and you have a device like you have there, you may have to service. Is there a strategy of laying the heat trace down so it can kind of be unwound off of the pipe, so it doesn't like coil around the pipe, making it almost impossible to just pull that one section loose so you can remove that device, kind of loop it around. That way you can uncoil it off that device.
Absolutely. When you do look at one, that's a great question. Thank you for asking that. I'm going to have Jeff hold the phone so I can maybe give you a little bit of better visual.
With the flow meter here?
Yeah. So we're looking at this valve. Right here. So I believe what he was asking is there a specific way to apply the cable to something like a valve or any item in here that you don't want trapped? For example, like you mentioned, if you just candy cane around it, when you do need to pull this out, service it, it will lock it in, causing you to need to cut it to gain access to that valve. So what we would do is, for example, we have a valve right here. Let's say in this application, this valve requires 8 feet of heat trace. We'll just pick that number, or 6 feet, we'll say. When I'm applying my cable, I would come straight along. I would come down 3 feet, come up 3 feet, continue it, and keep on going about my job of installing the cable. So now, if I went down 3 feet and up 3 feet, and I left that loop here, and this valve required 6 feet, so there's my 6 feet. I would grab that loop, turn it into a figure 8, take that loop, and then begin wrapping around it like this, kind of like in a circular motion. That way you can easily do the reverse, pull that loop out of the way, and gain access to your valve. So hopefully that answers your question.
No, absolutely does. And it just raises the importance of having installation, operating or procedure to your installing contractor that's how that's to be done.
Absolutely. It's a what you're mentioning is a constant battle, or I'll call or effort on my part and our part is to educate everyone through the entire process, from when you're designing a system with the engineer or EPC firm all the way down to when the material is on site. I almost always offer free training here at Eastern Controls on site, explanations of the design that for their specific application. And we also highly recommend isometric drawings. Very often the heat trace isometric drawings is something that is overlooked and is not deemed as very important, when really once this heat tracing is in and it's insulated, you have no one's going to remember what's going on underneath there. And if there is a problem, these digital controllers like you see here are great and really help point you in the right direction, but you don't really know what's going on underneath there without any record. So I highly recommend isometric drawings on all heat trace jobs, no matter the size, and also installation training. We do that. And that's one of the main support activities I get involved in, was with actually the guys that are going to be putting the cable on the pipe, not just how to wrap valves and flanges, but also how to lay out the job, pay out the cable, other tricks on using the tape, matching up your components and wiring components before it's mounted on the pipe. There's a lot of different tricks and things that really make the job go smoother, as well as the isometric drawings being a huge plus for installation, in that we have designed the system to be installed in some way. And that doesn't necessarily mean that's the only way to attack that project, but we want to make sure that what we provided is in line with what they actually do, which is another great benefit of the isometric drawings.
I can believe it's also important for determining the length of cable heat trace that's needed for the project, so you don't have a bunch of splices that are unnecessary.
Yes, yeah, there's a lot of things where, for example, I was at a job last week and there was one main header, like a 12-inch diameter header, and there were numerous different size pipes, offshoots of that header. And the assumption was that at each of those offshoots, no matter how long they were, they needed to tee, meaning put in an extra component, adding an extra splice, and then adding an extra end seal, when really they were short enough and better off just looping back and continuing to go. Therefore, not only saving them money, but saving them labor in the splices, and also reducing the amount of splices in the system, which obviously are a potential point of failure in the future.
So it sounds like worker training is essential, and would pictures of the project help also, picture file?
Absolutely. We have, for example, the isometric drawings tie into a lot of different things as far as being designed properly, communicating properly, also executing the job. For example, in large projects, when I was managing them, I would basically have teams of men, and then they would be assigned certain ISOs. ISOs 1 through 10 is this team, 11 through 20 is the next, and they're responsible for each of those. And then the idea was mark those up, and we couldn't check those boxes off until everything was inspected, tested, and photographs were taken. That's great to talk about. That's the perfect world. It doesn't always happen, but that's what we always drive towards is perfection.
So that may then be a team to take care of that part of the project.
Absolutely, absolutely. So with the services of the company that I came from, that's basically what I was involved in for the past close to 20 years. We were a manufacturer of the heat trace. We were the engineering firm for the design of the systems, but we were also, and still are, the company I used to work for, a full turnkey contractor for the design, supply, and installation of these systems, as well as the insulation of the piping and vessels and equipment. So we would take the whole project on turnkey or simply provide material and engineering. So that's all. I'll let Jeff get back to his portion, and I have some slides coming up with some additional details on installation and really the fundamentals of heat tracing and kind of the mindset that goes in behind it.
Ooh, good show. All right, I'm going to share screen. Give me just a second, please. Let me see, Ryan. We'll get it together, folks.
And just for our educational purposes, did that video turn out clear and was that helpful?
It was clear on my end, so I don't know if the other users had the same experience.
It was clear on my end as well, Ryan. It was very, very helpful. Yes, thank you.
Okay, thank you.
It was clear also on mine, so thank you. The audio was really good.
I thought that was helpful. Yep.
Yeah, that was helpful.
I underestimated the value of a picture. Just stating it only was 1,000 words.
We get excited about heat tracing. Ryan gives a tough act to follow, but we'll do the best that we can. So thanks everybody for being here today.
I've seen you dance.
What's that?
I've seen you dance before, Jeff.
It ain't pretty, man. It's not pretty. So I have to give this disclaimer. This presentation is intended for educational purposes for ISA St. Louis section. The materials from Jeff, Blair, and Ryan Duffy, and hopefully everybody can read. No responsibilities assumed by Eastern Controls for any consequences arising from the use of this material. Now we've got, if I may, we'll move on a little bit here. We took the roles of reporters here. We dove into basically the NERC and the FERC things we could find regarding what happened in Texas City. We used to talk about that. What happened in Texas in 2021, and there's a little bit more behind it. But what we're here today is to plant some ideas with you. We know, there's a lot of smart people on this call. Talk to your vendors, talk to your suppliers, talk to your engineers, talk to people who are out there in the field, and and look up some of the NERC and FERC stuff on your own. You as end users, as salespeople, as engineers can make the best decisions, and that's what we highly encourage. So if I could, one more survey. This is interactive. We've got a couple more of these. If you go to pollev.com/Jeff Blair 918, we don't need your name or number or dimensions or anything like that. Or if you're working on text, you want to do an SMS text, you text whatever answer you would like. So for example, if you want to learn about tips and tricks for winterization, you text 154820 to 22333. So I'm going to take the poll myself because I know what I want to learn. And the presentation is what the presentation is today, but what Brian and I will lift and shift as best as we can to focus on some different things as much as we can change things around. We do appreciate your feedback, and this helps us consistently get better for future presentations. Nice. What happened in Texas? Professional development. No, you're good. You're good. We'll give it just another couple of seconds here. Capture that. Cool. Well, thank you. So we're glad to help with professional development and continuing education. And I hope you all find this informative. So first of all, we try not to be political. And it's almost impossible when you look at, if you flash back to a year ago, what happened in Texas was absolutely political. You had Ted Cruz on the news going to the airport. And I know they did a pretty good roast of him on Saturday Night Live. I want to give the disclaimer. We tried to be non-political. We tried to look at this from all sides and figure out what happened and stick to the facts as much as we can. Some of the things we'll talk about briefly that I think you need to know, you'll hear these terms over and over again today. NERC is the Electrical Reliability Organization for North America. They are subject to oversight by the Federal Energy Regulatory Commission, or FERC. NERC is a non-government entity, and when I think of NERC, I kind of think of it like ISA or NEMA. They're not a government agency, but generally they're a conglomerate of end users and things who form an industry group, if you will. So that's NERC. FERC is the Federal Energy Regulation Commission. They are a government agency and they have jurisdiction over NERC. So NERC and FERC, those are a couple things you'll hear. And maybe if you remember from the news last year, one of the things you heard a lot of, the acronym was ERCOT, the Electric Reliability Council of Texas. Membership-based nonprofit corporation governed by the Public Utility Commission of Texas, also called the PUC. That's a non-government entity. So out of the three, we've got one government entity, and that's FERC. But just like with ISA, and ISA has standards, you'll see NERC standards and NERC recommendations and things like that, but they are not a government entity. So the three perspectives we see, Ryan and I are vendors. You see, we're here in our office today. You got to see our showroom, our process training unit today. We're vendors, but we try and stay objective and look at it from all different sides and angles. When vendors look at what happened in Texas and what happens with winterization and things like that, we all have our muscle memory. We fall into standard practices of, oh, this is, it's going to Florida, it's going to Louisiana, it's going to Texas, do it like this, do it like this. If it's going to Canada or up here in Philadelphia or Chicago, St. Louis, where it gets cold, this is what you want to do. We all have those faults. We all have our standard practices. Sometimes they serve us well, sometimes they don't. What we are trying to do as vendors is be out there in the field, do programs and things like this to get feedback from you on what your needs are, what you're trying to know, and what you want to know. But truly, we see opportunities for sales and things like that, of equipment, of consulting and things. So I think, and similar to everybody on this call, we're all trying to work together. We're trying to get to the end users. We're trying to make our customers more resilient. When we talk to engineers involved in the design of winterization and protection of gas power plants, they're out there, they're writing the specs, and Ryan's going to address that in a little bit. That's an issue that we think we could see a potential improvement on from the industry. And just like salespeople, what can we do to help? The engineers, sometimes they're bound by budgetary restrictions. This is the cost. This is what we're going to pay for you to design the system. But like we talked about when Ryan was walking around out here with the camera, those drawings, the upfront planning, the questions from Darren and Milton, all those things come into play. The more we can work up front with the engineer and have a really good plan during the planning phases and the drawing phases, generally the better the execution. But engineers, they're trying to help their customers as well. They're hired to do a job. They're hired to do the design, work between the vendor and the end user, and they have to make it work. The end users, when you're an end user, you're looking around at the other end users. I remember working with some power companies during the scrubber craze, say I guess it was the early 2000s when, you're putting a scrubber in on your coal-fired power plant. A lot of the end users are waiting to see what other end users did, what the government told them to do, what the local jurisdiction told them to do. And you're going to find a lot of similarities with that and with the winterization and weatherproofing that we're talking about today. What are my peers doing? What's happening? But make no mistake about it, just like every business is in business to earn money, the end users are there to make money. They want to be profitable. They want to do it as safely as possible and maintain their profits at the same time. But they're looking out for, what is the government going to tell us to do? Are we going to act before somebody tells us to do something? Do we need to know what to do? Are we going to be fined a penalty? What happens if we do this? One of the interesting things about 2021 is there was kind of a crystal ball in 2011, looking forward to the future. And this happened actually in Texas. We could title the presentation, What Happened in Texas in 2011. Back in 2011, they did have another freeze. And what they learned from the freeze was they lost energy, they lost megawatts, they lost power. And it was primarily from natural gas production, from gas producing power plants. And what happens was they actually had freezing where the water was mixed with the natural gas in the lines, and the lines would freeze. Believe it or not, they had icy roads of all things. You don't think of that too often, but when your operators can't get to your to the plant, some of these plants are unmanned, and when they have problems, you can't even get to the plant, get supplies to the plant, get things to the plant to get it up and running again, which led to rolling blackouts. And of interest was that the electricity and the natural gas were intertwined in that so many of the compressors were powered by electricity. So if you're not generating electricity, you can't run the natural gas. I'm going to pause here for just a second, and hopefully you all can see the screen okay. It looks pretty good on our end. This data, try and bring up my highlighter here. And we'll do a laser pointer. Here we go. So this comes straight out of the FERC report that we'll give you at the end. We'll have all the links and everything. But they talked about, the FERC report highlighted frozen sensing lines. If you think about that, well, what are they? Well, specifically, they lost 15,000 megawatts in 2011 due to frozen sensing lines for drum level sensing lines. In other words, boiler drum level. And then not sure what these are, other sensing lines. So about 15,000 megawatts just of frozen sensing lines alone. If you think of that, that's a traditional usually I think of a differential pressure transmitter with a couple impulse tubing lines, things like that. Other causes, frozen equipment, frozen water lines, etc. So staying on 2011, this is the actual FERC guide. And again, we'll put a link we'll give you a link at the end. There was an interdependency of electricity and natural gas. The compressors run off of electricity. If you're not generating electricity, you're not producing gas. So they had an intertwined effect. The loss of one affected both of them. And to boil it down at the end, what FERC said was their final report regarding 2011, complete paragraph, but I'll just paraphrase here with the highlight. The single largest problem during the cold weather event was the freezing of instrumentation and equipment. So you fast forward to 2021, or for us, we can look back to last year. This is a rough breakout of Texas's power generation capacity, where their power came from about the time that the freeze happened. So almost 53% of their electricity came from natural gas. So what actually happened in 2021? The megawatts they lost vary depending on which report you look at, but generally it's between about 40,000 megawatts and 55,000 megawatts. This report, they talked about 40,000 megawatts or 40% of thermal generation. They had to cut load, and it goes back to some of the same reasons that happened in 2011. Bad winterization, the guidelines were issued, but people didn't follow them, companies didn't follow them. ERCOT actually under forecast the gas demand, and ERCOT is a standalone grid, which we'll talk about in just a minute. The rest of the grid in the United States is essentially interconnected, where if you're short power in St. Louis, they can transfer power on the grid in a simple matter of speaking. So this is Bill Magnus. He's no longer the CEO of ERCOT. He was fired shortly after a congressional hearing. And this is the source here. You try and put yourself in his shoes, and this is his quote directly out of his testimony before Congress. And he said, "The work is done with one purpose: to maintain the 60 hertz frequency that is needed to ensure the stability of the grid." I'll stop there. And I really thought about this, that I'm not defending this guy. I'm not condemning him, but based on that statement, I think he feels like it could have been a lot worse, because there were some plants that did still operate in Texas. So he said ERCOT, for whatever job they had, they were trying to juggle and make things so they didn't trip the whole grid off in Texas. This was the after action review from ERCOT regarding what happened in 2021. And it's right off their website, ERCOT.com. You'll have the link at the end. But it came down to enforcement. Essentially, ERCOT could conduct site visits, they could do spot checks. But when it came to, at the end of the day, they really didn't have the teeth. Remember, it's a user group, ERCOT. They didn't have the teeth to go in and say, you need to fix this or you're going to get fined, $10,000 a day or whatever it was. It was up to the only entity that can confirm that a plant is weatherized to any particular standard is the entity that owns or operates the plant, period. So they can come in and make recommendations all day as, hey, you really need to put the heat trace on, you need to do this insulation, you need to put up some wind barriers, you need to protect this, that. The only entity that could do that was the end user. They could tell ERCOT, you know what, we're good. We're good. Now, there was unfortunately a loss of life in 2021, and this is a testimony from the mayor of Houston, Texas, Sylvester Turner. And any of us who have ever lived in a cold area and had pipes freeze and things like that, the loss of life is the worst thing possible that can happen. But I mean, having your pipes freeze is a first world problem compared to that stuff. But they had, people died because they were without power. 50,000 homes and 400 apartment complexes had broken water pipes. People passed away from hypothermia or carbon monoxide poisoning. So he obviously, very emotional talking about what happened when they didn't have power. And this is the NERC president, James Robb, his testimony before the same congressional subcommittee. We talked about the 40,000 megawatts before. Here you see he says it's 52,000 megawatts or 48.6% of installed capacity. But again, boil orders, they couldn't get natural gas, lives were lost. The recommendation was legislation from Texas. And this is where what happened in Texas gets a little bit muddy. When we wrote the presentation, there was still legislation pending in Texas. I think it was passed by the Texas House of Representatives. Because we're in Philadelphia today, I know we got some people in Indianapolis, St. Louis, and all over the country. The best guidance we can issue, or for educational purposes, is look at what your local regulations are, look at what your state regulations are. Before don't rely on what's going on in Texas, obviously, but they passed legislation. But again, it goes back to, does it have any teeth? What's their enforcement to come in and actually make those changes or fine operators that aren't doing the right things? This is just a brief overview. I'll play this video. Corey, if you could give me a thumbs up if this audio works. This is like a 30-second little video that just kind of goes through the different tools as what you could recommend for some of the equipment.
It's really low, Jeff, the audio. I heard it at first and it kind of went away.
Can't hear it?
No.
No, can't hear it.
All right, we'll try it again. Is that better?
No.
I think you might have to share your audio as well as share screen.
Okay. You know what? I think we'll punt on this one.
Just walk us through. You watched it, Jeff. Just walk us through as it's going.
Sure. Covering coal piles. There's the heat trace that they call heat strips in this, which upsets a good wind barriers, protect from the cold wind. Watch the liquids that may freeze outside. Inject antifreeze if needed. Oops. Wind barriers, heat trace, and injecting methanol. And separators. So just a few different methods of protection there. And Ryan will hit on some of these again in the second half of the presentation. Is the audio okay, Corey? Can you hear me all right?
Yeah, I can hear you all right. Sorry
Okay,
about that.
No worries. Thanks. So this result from NERC, they sent out a survey, and Ryan and I actually got a copy of the survey. And maybe if some of you are working in the power industry, you got this survey yourself. And it essentially asked, what are you doing for all of these different things? And these were things that were part of the problem in Texas. What are you doing for your fuel supply, your backup, your primary and your backup fuel supply? Are your natural gas suppliers able to get to the site? What are your ramping rates? What are you doing for weatherization? What about solar panels, emissions, blah, blah, blah. And then they finally came out with an actual recommendations. And this was a framework NERC did. And this was about the best deliverable we found in terms of what happened in Texas in 2021. What should you do? What were the problems? Where are the problem areas? And this is just a brief summary. The typical problem areas they had remarkably similar to 2011, the drum level transmitters, the condensate level transmitters and the sensing lines, the pressure transmitters on the gas turbine combustor, steam flow transmitters, and then different types of valves. So winterizing those things is exactly what they recommended. There was one good thing, one good story that came about back in 2021. And that was actually El Paso, Texas. So if you look at if you can see the outline here, that's the area that ERCOT is responsible for. So essentially in the, up in the panhandle here and over by the Louisiana border and then over by New Mexico, that does not fall within ERCOT. When you start looking at what El Paso did back in 2021, after 2011, they implemented all the changes that the NERC and the FERC recommended after 2011. And that was winterize their existing stuff. And they actually built a new power plant, and they built it based on the worst possible conditions they saw in the time of Texas, a -10 degrees F. So what this little chart, it was pretty cool. This is from not from a government source, but texastribune.org. The dark areas represent the darker the area, the less power they had during 2021. So the area, around Austin, the area around Houston was the hardest hit. Northwest of Fort Worth here was pretty bad hit, but obviously the light areas, El Paso, up here toward the Panhandle, they actually fared pretty well during 2021. I know ISA, we probably have some.
Jeff,
Yeah.
question about that, about the El Paso. Was it like the El Paso City Council passed a law, or did they just voluntarily accepted the recommendations.
Yeah. Michael, I'm going off of memory here, but they were on a different grid themselves. They weren't on the ERCOT grid, and I failed to mention that. That's one thing. If, let's say they didn't winterize, they could have potentially drawn power from another portion of the grid rather than relying just on the ERCOT grid had they not winterized. I believe it was like the El Paso utility was municipally owned by city of or county of there in El Paso. I'll have to look that up to confirm.
Thank you.
Okay. Yeah, Michael, sure. Good question. But if you want to dive in a little bit more on what, outside the power industry, the Chemical Safety Board is a great resource. And on their website, they talk about, we're all in the instrumentation world, we're all familiar with dead legs. They have some horror stories of dead legs actually filling with condensate and things like that, unintended because of a leaky valve or something like that. Filling with condensate, freezing, and the nasty stuff busting out and causing an accident, unfortunately. So their simple recommendation, and I encourage everybody to take a look at this. Dead legs must be surveyed, removed, and effectively isolated from hazardous process streamed or winterized with insulating and heat tracing. So what we're going to do now, I'm going to turn it over to Ryan. He's going to address some of the issues we talked about with specifications earlier, and he'll get into some of the technical aspects of the actual materials and things that we use for heat tracing and winterization. So I'll turn it over to you, Ryan.
Thanks, Jeff. All right. I have following this slide, I have some fundamentals of heat tracing, the thought processes going behind it, some of the design practices, and how the systems are put together. But before I get into that wild and exciting stuff, I like to talk about what I see as one of the major issues with these freeze ups. And it's not really you can point to as something specific or technical. It's about the way these plants are built and designed and the process of getting them built. And that, in my opinion, being in this world for as long as I have, it seems like when a new power plant is being built, winterization is sort of is a box that needs to be checked. And there's not a lot of always, but there's often not a lot of sincere intent to not just check a box, but to get this plant fully protected from winter weather. My example is that when probably a large majority of the times we're bidding a heat tracing system or an HMS heat management system on a new power plant, the first thing we see is the specification being put out by the EPC or the engineering firm or owner. And what they have is it's sections. There is a section on insulation. There's a section on heat trace. There's a section on electrical. And it's kind of and mechanical. And there's information that you need from each of these sections. And we're kind of piecing it together like a puzzle. And so that's the first problem. What I would like to see is a specific section carved out for winterization that combines all of this and forces the designer, engineer, EPC firm to really look at this as a system, not a bunch of puzzle pieces. That's the first thing. The other thing is there's a really inexpensive and easy way to get a lot more mileage out of your heat tracing system, and that's through control and monitoring. I'd say a large majority of the plants, again, when you look at their winterization systems, they have majority freeze protection. It's not process mean. It's just we don't care what the temperature is. We just don't want it to freeze, which is fine. So what they're almost always doing is they're putting in group controlled panels. So there's basically just a power distribution panel with a main contactor, and that main contactor interfaces with a single mechanical thermostat that's out sensing ambient air. Mechanical thermostat senses, okay, it's getting 40 degrees Fahrenheit or cooler, slam that contactor shut and turn on all your heat trace. And that's typically how things are controlled at these power plants. And there is little to no monitoring going on at all. So what is that? What happens then is that you don't really know what's going on until something is frozen. You can have a line that's not up to temperature. You can have a line that is tripped. You can have a line that is the insulation integrity is not there. You really have no sight of that until there's a freeze up. When in reality, if you just switched out that control and monitoring panel, with something, I'm sorry, that control panel for a control and monitoring panel or something a little bit smarter, it's going to provide the ground fault protection for you. It will provide temperature monitoring for you. It'll give you remote alarming and local alarming. But most importantly, all of the smart controllers that we typically interface with, they do a really important feature that's very simple. Every day, they will check the integrity of the cable. They will energize that cable for a short period of time every day, no matter what the temperature is outside. So that way, if there is some damage, there is a problem, or if there's an outage in July and cable was damaged and it's not going to hold up, or it's going to trip over overcurrent or ground fault, you're going to know that day. Not all of a sudden when that contactor slams shut, it's cold out, it's calling for heat, and then you're getting trips. And then what is it? You have no monitoring, you have no real sight of why it's tripping. Is it overcurrent? Is it ground fault? Is it low temperature, high temperature? You really have no idea. So that really is the start of a lot of these issues that we see, and a lot of the frustration at the plant level is that, guys, things will be freezing up, and when are they dealing with it? When it's snowing sideways and there's ice everywhere and no one wants to deal with it. Instead of, if they had a little bit more smarter technology in the panels, they could really get well ahead of this, have time to address it. And that panel is going to point you in the right direction. Is it ground fault? Is it overcurrent? Is it low temperature? Is it a high temperature issue that damaged the heat trace? All that stuff that goes on that these control and monitoring panels provide. So before we get, I just wanted to point that out as one of the efforts that I have going on in one of the industry changes I would like to see is a change to the way these plants are designed and built right from the get-go, because I see a lot of problems. And at minimum, this idea that I'm talking about as far as being smart control and monitoring, if they don't want to do that with all of their lines, at minimum, put it on their critical lines. Which lines will trip the plant? Why aren't you having those monitored? Why is it just control and no monitoring? It doesn't make a whole lot of sense. I'll give you a real world example. I won't give you the plant name, but 2 weeks ago, we got a call. Plant tripped because of a frozen drum level transmitter, and it was the line. They had it on a mechanical thermostat, no monitoring, no control, didn't know what the problem was until it was frozen. Cost them, what they told me, $4.8 million in loss from this line. Now, I looked at them like $4.8 million. I mean, like, that's just one trip. And we proposed to come in full turnkey and repair it less than 100 grand. I look at the numbers, and I understand when you're building a plant, you want to be mindful of cost, but being mindful of cost also, really means, choosing the right places to skimp and not. I mean, this plant tripping and these millions of dollars being lost, it happens a lot. It probably happens a couple times a season that we hear about, that at least I hear about. And that's just in the Northeast region and plants that we're engaged in. There's other times that it's happening, I'm sure. So I'll just leave that, and then I'll move on to the next slide. Just wanted to talk about some of the things that the way I look at these projects as a whole, especially in the power industry. So now we'll get into a little bit some of the details of heat tracing itself. 10 minutes. I'll be quick. So applications, technology. So this is what we'll talk about. Strictly industrial heat tracing. That's the world I'm living in, even though I do get into a good deal of commercial. I'm going to talk a little bit about the applications in some of the industrial environments, the technology, the control and monitoring systems, and general winter preparedness. And I'll do this quick, so we're already running a little bit late. So why do we heat trace? Prevent freeze is the most common, prevent condensation buildup and crystallization. And also a good portion of our work is to maintain certain temperatures, whether that's to reduce viscosity or prevent a certain material from completely setting up or chemical reactions from occurring. Most commonly our applications are 40 degrees maintain or freeze protection, but there are numerous applications where, for example, we're doing some things with DuPont right now, and the maintain of their piping and vessels is around 600 degrees Fahrenheit. So those are the temperatures we can maintain easily. I've done the highest maintained temperature I've gotten into was around 1200 degrees Fahrenheit with heating cables. So we can, it's not just a freeze protection cable, which is what everyone's mostly familiar with. We can maintain vessels, equipment, and piping well above that temperature as well. So heat tracing, what is it? What do we use it for? How does it work? And what you shouldn't do. So basically, you have a bare pipe and there's water in there. Let's say it starts out at 40 degrees and it's -10 out. There's not a long period of time, less than an hour, that it would really freeze up. So what we're trying to do with heat trace, and I'll get into this a little bit further in the next slides, but we're not really trying to heat up an application. It's not a heat exchanger. What we're trying to do in most applications with heat tracing is maintain the amount of heat that's already existing in that pipe. Can we heat things up? Yes. Is it quick? No. So 9 times out of 10, we call it freeze protection. It's process maintenance. We're not trying to heat up a fluid process or a flowing process. We're just trying to prevent that heat loss. And I'll get into that a little bit more. So here's the one example. So we have a 3-inch diameter line, water's in there, it's minus 25 degrees outside with 30 miles an hour wind. Your heat loss per straight linear foot of pipe is around 100 watts a foot, which is, it's not manageable to try to address that without insulation. You have to get that heat loss down. 100 watts per linear foot would be a tremendous load on any system and wouldn't really make sense, which is the reason and the real need for one of the main needs for insulation on the piping. What I mentioned earlier, that everything must be insulated. One is to reduce the heat loss, and 2 is to make sure the energy coming out of the heating cable doesn't simply dissipate to the air. It's actually getting into the pipe. So now we look at a pipe that's insulated only and not heat traced. And often people will assume, especially in the residential, I get that all the time, it's like, oh, it's not going to freeze, it's insulated. Insulated will slow down the process of freezing, but it will not prevent it from freezing. I see that all the time. I've been on job sites when I was in the residential world, and they're like, oh, we're going to run these pipes on the exterior wall of the house in Philadelphia. And I said, okay, well, what's going on there? Oh, we'll insulate it. It'll be okay. Actually, no, it won't. It won't be okay. It will buy you time, but it will not prevent it from freezing. It will basically reduce the amount of heat loss coming out of that pipe per linear foot, but that heat will still be lost eventually. As you can see here, just same situation, minus 25, 30 mile an hour wind, 3-inch diameter pipe. We took no insulation, 100 watts per foot heat loss. Now we're down to 5 to 8 watts per foot. And that is a much more manageable amount to put heat back into. So that's what we do. We basically look at, and this is kind of this diagram here shows you a little bit about what I was mentioning, in that a non-heat trace pipe, that fluid will slowly get down to the temperature you don't want it to be. When you have a heat tracer on that pipe, all we're doing is trying to keep that temperature the same, not really ramp it up. And that's what we're up to with most of our stuff, is we basically calculate how much heat is going to be lost through the insulation per linear foot of pipe in when we're trying to maintain 40 degrees with certain ambient conditions. And we quantify that, and then we balance that with a little bit of extra heat for safety factor to put back into the pipe. So heat being lost, simply being replaced by the heating cable. And that's mostly what we're up to with heat tracing. Now, the heat tracing system as a whole, when we look at systems, what I was mentioning earlier, I like to get visibility of everything, is that when we see a heat management system or an HMS system, a lot of people will say, oh, well, I just need the stuff that's on the pipe. I want to get involved and understand everything back from the transformer, control and monitoring panel, distribution panel, your cable tray or conduit, all the way to everything on your pipe. I want to understand everything that's involved, because minor changes in any of these elements can result in a lot of cost savings. And so when we look at entire projects right now, I'll give you an example. Is a real world example is a project I'm working on now that is a 600-degree maintain. We had a project where they were kind of telling us, like, hey, this is what we want you to do. Design your system based on these parameters. Don't worry about anything else. And they basically said, this is what you have to work with. We have 600-degree maintain on a 4-inch diameter pipe, and we want 1-inch thick expanded perlite on there. So that's what we did. And then we came back with them. We did a design. There's going to be numerous passes of cable, very high load because it's a high maintain temperature. And they said, well, this is crazy. This is going to be over $100,000 for only X amount of pipe. That's cost per foot is just way too high. And I said, well, this is why we wanted to get involved earlier in that. And to give you an example, when we reran calculations for them. So everything is exactly the same. The voltage, the maintain temperature, the minimum ambience, everything's the same, except for we went from 1 inch to 2 inches of expanded perlite. We just increased that insulation thickness. So what does that mean? Less load. Less load means less power circuits. Less power circuits, less control points, smaller panels, less equipment, less junction boxes, less installation labor. Just in the engineering and supply of the equipment, it went down almost 50%. It almost cut in half by changing one design parameter, being the insulation. So it's easy to us for us to see that, and we see it all the time, but people that are involved in it say, no, this is our plant spec. Plant says 1 inch of this, and that's all we're going to get on there. And we don't care if there's more room for more, it's 1 inch. That's the kind of value when you really look at these systems as a whole, as opposed to as a different saying, look at our insulation spec in this section, look at our heat tracing spec in this section, and just do what it says. When you really look at all these together as a system and not different puzzle pieces, you can really have a lot of savings. And on top of the savings, you have less cost of equipment, and then you'll have a more reliable system at the end of it, which is really what we're driving towards, to educating the industry to really think of it this way. So self-regulating cables, I'll get into that technology a little bit because that is most common. Today, I'll talk quickly about self-regulating and our mineral insulated cable. So self-regulating technology is the magic, we'll say, in this cable, in this industry with heating cables, in that the actual cable itself, hopefully, can you guys see the mouse pointer here? Is that visible to you? Okay, thank you. So actually, no, when you look at these cables, you'll see numerous layers: outer jacket, braid, insulating jacket, and you have your heating core and your two elements. I'll explain a little bit about what's going on. These two conductors here are strictly current carrying conductors. They're not heating elements. They are not resistors in any way. They are just delivering power down the run of the cable. The actual heating element is this extruded. When you open up this cable, it looks like a black coarse plastic. Oh, sorry about that. Looks like a black plastic, and that's actually a semiconductor, and that's really what's actually creating the heat. So what's going on here is, when this black plastic is extruded through these two conductors, let's say it's 120 volts and there's your neutral, you have conductive paths going between here and that conductor all along the length of this cable. Now that conductivity of that plastic, I'll say, or that heating core, that conductivity changes based on temperature. When it gets cold, it contracts, and it becomes more conductive, creating more heating elements all along the length of that cable. When it gets hot, it expands, creating less conductive paths, therefore putting out less heat. So that's how the cable self-regulates itself. Now I'll say self-regulating, and that's what it's called, and that is what it's doing. But keep in mind that it never shuts off. It will reduce its output and it will increase its output based on the temperature, but it will never completely shut off, which is why there is a definite need for control of this cable. And I'll talk a little bit about that in that before I start talking about the MI cable, and that the most blaring example and the most common issue with self-regulating cable, is we see a lot with safety showers. And safety showers, obviously, being an important item of a plant, being a safety issue, people start thinking, okay, I'm going to put a self-regulating cable on there, and I'm not going to put any control on there, because if I put a control or a thermostat or something in there, that's another point of failure, and that could reduce reliability. So I'm just going to let it go, which is somewhat of a sound idea. The problem is the self-regulating cable, even if it gets very hot, it will still put out power. So if you took, for example, a 1-inch diameter copper pipe, and you put on our minimum output cable, which is 3 watts per linear foot, and you let it cook, no control, it can easily get that temperature of that pipe up to 120 degrees. So I've gone to plants and I've seen them test it, and they pull the chain to test the safety shower, and steam has come out. So imagine going for an eye wash or a safety shower, and you're basically getting doused with 120 plus or even more water. You're maybe even creating even a worse problem than what the person was going to the safety shower for. So I always recommend control, not just to, I think maybe some people think, oh, this guy's in sales, he's trying to sell me something extra, when I'm not retiring early on selling people thermostats. I promise you, you need to control that heat trace for numerous reasons, that being the most common. So then I'll get into the next major technology, especially in the power industry, which is our mineral insulated cable. And basically this is a metal and magnesium oxide is the only thing that's going on in here. There's no plastics, there's no rubber, there's nothing in there. So basically, when we make this cable, it starts out with, say, a 1/2 inch or a 3/4 inch diameter pipe, heavy wall, and inside there's a 12 gauge conductor, and it's a tube in that pipe, or a conductor in that pipe, and we extrude it, and we pull it out, and we stretch it over and over again, until the outer diameter and the inner element, that 12 gauge conductor, becomes very, very small, 18, 20, even 22 gauge wire. It can be as thin as a hair. And what that is that's a heating element now. Now it's basically just a resistor. So why are these cables used? with the self-regulating cables that I discussed just a moment ago, they have certain temperature constraints. They can maintain certain temperatures, but most importantly, they can only withstand up to certain temperatures before they degrade, or even completely melt. It is a plastic product. So when you get into power plants, for example, your HP drum lines, you have some really high temperatures involved. And then some people think, well, if it's so high temperature, what do you need it for freeze protection? Sometimes, and a lot of times these power plants, this heat tracing is only really needed when the plant's shut down and not running. But if you need it, you need it. You can't be cracking pipes all over the place. So an MI cable can do the same thing, freeze protection, but also give you higher exposure temperatures and still without breaking down. Different types of control. I'm sorry.
Is there a certain temperature range that you want to use an MI cable? Like if somebody comes to you and they're like, hey, I got this is how we're designing this process, it goes, the process lines are going to be at 250F. Is there a certain point where you're like, okay, I'm going to use this, or I'm going to self-regulating, or am I going to use a MI cable? Is there a
absolutely? What you're getting at is a very fundamental question, and a question we should be and always asking. Two of the main ones are what you're getting at is, one, what temperature do you want to keep the pipe at? And two, what temperature is my cable going to be exposed to during your normal process or during a cleaning process? So and people will say, well, I don't want to use an MI cable. And I say, either do I. And MI cables are made to order. It's custom. They're not in stock. They're harder to install, and they're harder to repair. So when I have MI cable, I have zone heaters, I have a bunch of different technologies at my disposal. MI cable is typically the last option I'm choosing for those reasons. I'm always driving towards, can I use a self-regulating, cut the length product that I can just ship out in the field? It can be terminated easily. That's what I'm always driving towards. So when there's an MI cable application, it's not because of preference, it's because of necessity. And that necessity is typically either you have a really high maintained temperature that we can't maintain with a plastic product, or you have a process that has a very high exposure temperature that would damage our cable. When those two, either one of those situations or both of those are met, then we go to an MI cable option. So control and monitoring, I know I'm running a bit late. I just got the warning, so I'll be really quick here. I apologize ahead of time. Ways to control. Line sensing and ambient sensing thermostats, group controlled panels, which you see on the middle and the left, to our smart controllers, which you see on the right. This one right here is one we saw earlier, which is a single control point, which monitors voltage, current, amperage, provides ground fault protection, monitoring remote alarms, local alarms on a single point. And then we have our this does all the same things, but in multiple points, up to 120 per single enclosure. Last thing I'll talk about here is tube bundle. So very quickly, when it comes to tubing, tubing is people will have a misconception in that installing heat tracing on large bore piping can be more difficult than small bore, when it's actually the opposite. Applying your heat tracing out in the field and properly insulating and sealing that up is much more difficult on a small bore tubing than it is large bore. Large bore, it's easy to get your hands around it. If there's plenty of space to put that cable, there's an easy way to tape it. The bends aren't as tight, so you can get good contact around corners. When you have small bore tubing, you're trying to always kind of get good contact with that heating cable, and it's very difficult. The bends are tight. There's not a lot of space. Sometimes the actual heating cable is larger than the actual tube you're tracing. It can be very difficult. So one great option is what we call a preheat traced and insulated tube bundle, which is basically we get in early and we understand what is your specification for tubing, what do you want to maintain, all the typical stuff that we do for the piping. But what we would provide is one product. The product is the tubing that you need, the heat tracer, the insulation, and an extruded polyethylene or PVC jacket on the top of that. So now when your guy's out there in the field, and how that would typically be done is a guy would run your tubing, terminate your tubing. Another guy would come along, apply the heat trace, terminate that. Another guy would come along, insulate, wrap it all up, and paint it with mastic. So you have a lot of people touching the pipe, aren't really working together. They're different trades. No one's really thinking about the same type of goal, which is to prevent it from freezing, and things get missed. Now, with the tube bundle product, albeit that the product is more expensive, you have one guy basically running your tube, your heat trace, your insulation, and your jacketing all in one shot. Now they may be a couple different trades terminating it. Your mechanical for the tubing, the electrical for the electrical heat trace if it's traced that way. But at the end of it, you save in labor, and then at the very end, you have a much more bulletproof product in that it's that extruded jacket, really tight cable to the tube, and everything's all really nice and neat. I'm 100% more confident with tube bundle than I am conventional ways of freeze protecting tubing. And that tubing obviously as an example here, will terminate into a heated enclosure for a transmitter like you see here. And now I will kick this over back to Jeff. Hopefully that wasn't too quick or boring, but I'll kick it back over to Jeff for you guys.
Thanks, Ryan. Yeah, we're proud of the enclosures here and proud of the process training unit. Maybe you saw it in some of the video we shot earlier. This is a typical method of providing weatherization for a differential pressure transmitter. You put a heater in the box and a clamshell enclosure. So I'm not playing to the home crowd with this slide. This is one that I use in several ISA presentations. I'll let you read it, but Corey, I know you knew Vernon. A lot of us did in St. Louis, and I think there's, when you Google Vernon and ISA, there's several quotes and things that come back from him, published articles. He did the Autobach, but he talks about vendor support and the ability of a vendor to educate its customers and work with the customers, not only just to sell more stuff, but give them the background of the who, what, when, where, why we're doing those things. And I place a lot of respect in what Vernon says. So we'll skip the last survey. Corey, I could give you a copy of the presentation if you'd like for ISA. The links are in here. I put a couple links in the chat. And before we adjourn, I'll look at the chat notes here and see if there's any other questions. What we'll leave you with, if you would like a copy of Winter Top Tips maintenance checklist, just email us at marketing@easterncontrols.com. Mention Winter Top Tips in the subject line, and we'll send a copy to you, please. Corey, I'll turn it back to you, sir.
Yeah, appreciate it, Ryan and Jeff. So thanks for the presentation and the walk through the demo there. I know we're a little bit over, but if there's any questions, please feel free. Go ahead and open the mic and ask now, and get your questions in the chat if you can't get to unmute the mic.
Blow it up here. I don't know if you could all see the chat. Actually, Corey, I'll stop sharing my screen. Give me a sec. Here we go. Here we go. Stop share.
Say the last comment I've got is be sure to check out ISASTL for .org for those of you interested in upcoming presentations. On the 23rd, we have from precision agriculture to prescriptive agriculture or global restructuring of the food system coming up on the 23rd. On the 16th of March, we have a program on optimizing HMIs, tips and tricks. We're actually going to have a time change to that program, so stay tuned to your emails and ISA Connect on that one, but same date, the 16th. Not seeing any questions come in the chats. Any questions out there in Zoom land?
We're seeing one from Michael. What was the name of the last heat trace? Michael, I'm not sure if you're talking about the tubing bundle or the MI type cable, or
May have been the MI. It was in M as in Mary, I as in instrumentation. That was a good one. But it was magnesium oxide insulated MI is basically what that is.
Yeah, I think it was the tubing bundle. It was pretty much the last slide you were guys kind of talking about.
We call that tube bundle. It's basically a tube bundled with insulation. It can be bundled with a steam tracing tube, an electric tracing tube, nothing at all, just insulation at all. It can be just a PVC jacket. It's a custom product that's made to order for pretty much each application, but it's a pre-insulated tube bundle.
if you want a specific brand name, O'Brien, it's an Amatec company in St. Louis, actually makes it. The one we sell as Eastern Controls. I'm sure there's several out there, but one we have is O'Brien, which is, I think it's made in St. Louis.
Yes, it is. And if you have any questions about it, you can reach out to me, or I can send you some information, whatever you like.
Is that typical for most plants to use the pre-insulated tubing bundles, or do they do the traditional method typically on their air instrument lines, or how does that work?
I see more conventional than I do see the tube bundle, unfortunately, and we're trying to
You
drive
do.
it for various reasons. But in some situations, depending on the length of the run and the configuration of the tubing, how often it's terminated, sometimes it doesn't make sense to do the tube bundle because of you have to it comes on a big, large reel, like a 5-foot diameter reel, and you're
Yeah.
basically pulling it off and cutting it with a hacksaw, and then you're splicing it back. When there is let's say a run with a need to splice it every few feet, it becomes very difficult to install and very expensive. So there are some applications where it's not the best idea, but most of this stuff, especially in the power industry, it really makes a lot of sense to use a pre-insulated tube bundle for all their instrumentation lines.
Okay, thanks. Appreciate it.
No problem.
Bob Hyder, we see you there. Ryan, maybe you're familiar with the weather barriers. I'm not that familiar with them. Bob is he's an ISA fellow. He worked with a major manufacturer in the St. Louis area for years as a process control guy. I don't know if you dealt with weather barriers before or not.
You actually had a problem with weather barriers, or they just did not have any weather barriers?
They got wet.
Yes, water and and that's the biggest enemy of all of these winterization systems is moisture, which is one of the reasons I love the tube bundle is that you have an extruded jacket, PVC jacket. There's not really any holes in it. So when you look at the tube bundle product, you have that extruded jacket, and when you do need to splice it, there is a boot that goes over it, and it's a heat shrink boot with a glue involved. It's a very sealed, tight, dry system, which is really why it's so powerful, as opposed to doing tubing and wrapping it with a fiberglass tape and then coming back and painting that with a mastic for your water protection. It just puts the human element in it, and it's not as good as a system. Now, when it comes to the piping, that's another barrier in that the jacketing is really important to keeping everything dry, and how you install the components and how you seal it up. And part of your winter preparedness each year should be not really going out and testing things electrically, but really a visual inspection of the integrity of the insulation system is just important, if not more, than the electric heat trace.
Are there companies that specialize just in installing heat trace? Is that a typical thing that you'd see, like, versus versus a mechanical or electrical, or the plant themselves doing it? Would that be a suggested route if you're doing it a traditional way?
Absolutely. And I'm glad you mentioned that. And that's pretty much my world. When I was with my previous company for 18 years, that's what we were. We were a few things wrapped into one, to give you an idea. We were a manufacturer, Raychem being the brand that we represent here at Eastern and that I worked with. I worked with Raychem for about 18 years, but we weren't just a product manufacturer. We were also an engineering house for the design of the systems. But just as importantly, if not a majority of our goals and our activity was involved in the design, supply of the equipment, and the installation of the electrical portion, as well as the insulation. So we were a manufacturer and specialty contractor for HMS systems, or heat management systems. And we're not the only ones out there that really specialize in that. There's a handful of them out there. But that was, I'm proud to say that we were kind of the ones that really started it. And some of our competition out there kind of saw the model that Raychem and the installation division called Tracer Construction, what they did and what they created, and then a lot of other companies followed suit. So yes, to answer your question, there are companies out there specifically involved in winterization and HMS systems, specific to heat tracing design, supply, installation, and insulation work.
I don't want to be respectful of you guys' time, so why don't we take, if there's one more question out there, we'll limit this to the last one. And once again, appreciate both Ryan and Jeff for presenting today. Lots of great information and very timely with the winter storm we had just last week.
Yes. I actually have heat trace in my gutters too, right above my driveway.
So call Ryan if you want to hook up.
Exactly. I don't recommend anyone get the snow melt in their driveway. I don't have it. I could get the snow melt equipment for free,
and I still don't have it because it's too power hungry. I'd need to contact the utility for an extra service to be brought to my house to heat my driveway. It's very power hungry. It's looking like 35 to 50 watts a square foot.
We don't get enough snow here for that to ever pay back. So,
well, we were talking about sports earlier. The only job that I designed and we actually installed snow melting in a residence was in Philadelphia, Alan Iverson's house. He got it, and I think his system, just the snow melting system alone, required a 225 amp main circuit breaker. So that was just for his snow melting system. But I don't have Alan Iverson money, so I still shovel.
All right. I'm not seeing any other questions. So with that, I think we can adjourn for the day. Thanks again, gentlemen. Ryan, pleasure meeting you. Jeff, always great to see you. Appreciate everybody dialing in today, and looking forward to seeing everybody on the 23rd for the next presentation. So thanks again, Jeff and Ryan.
See you, Corey.
Thanks,
Yeah,
guys.
great job,
Take
guys.
care. Any questions, give us a buzz.
Appreciate it.
Yeah, thank you.
Thank you.